Okay, so this is a video for the second problem on the second group work, and it's about the circuit. It's a simple circuit, just an RC circuit where the capacitor, I don't think actually, oh yeah, I did say it's charged initially, so there's some amount of charge. I didn't give any values for it. I'm going to just solve the problem using the R's and C's and whatnot. So the idea is we want to first, and many of us know the answer to this. We've had physics, so we know what happens to this charged capacitor. But suppose we don't, or suppose we're solving a more difficult problem. We'll do Q prime versus Q. And so it's going to help take this differential equation and kind of move it around a little bit. If we solve for Q prime, we'll have Q prime equals minus 1 over RC Q. Now, one of the things you can tell right away from this is that since Q prime has units of coulombs per time and Q has units of coulombs, RC must have units of time. And we'll see when we start solving these with integration and stuff that, and you probably remember from physics that this is a time constant. So when you're solving these equations and you find units that cluster together to form things like time or length, usually there's some sort of characteristic property of the system. And you can pick up on that just from unit analysis. So in any case, this is a very simple line. It goes through the origin with some pitch, right? The slope is it drops 1 for every RC you go over, all right? Well, not, I mean, and so the equilibrium is here at Q equals 0, Q prime equals 0. So if you don't have any charge, none of it flows. You have no current. Right? And so we can use this to sketch solutions. If you start with a negative charge, well, you're going to have a flow of current one way. If you start with a positive charge on whatever the plate, you'll end up with a current the other way, essentially. And so here we go. Let's use this as a stable equilibrium. The system is going to tend towards this solution. If you're already there, nothing happens. So if we do Q versus T, then it's this line, that's the equilibrium, and we can tell, starting with some amount of charge on it, right? Well, what's going to happen to that? Well, it's going to decrease. We have a negative derivative, and it's going to decrease less and less and less and less, right? So starting from some Q0, it's not a straight line, right? We're decreasing, but decreasing less and less and less and less and less and less, all the ways we go across, all right? Now, of course, one thing I should point out here is this equation is really identical in form to the dp dt equals rp for population growth, for exponential population growth. Right? So we'll see this a lot in this class where equations in very different fields have an identical mathematical form. So there's that same kind of thing, exponential growth or exponential decay. It's a simple differential equation, but it has wide applicability. Right? So we'll see lots of solutions like this. Now the follow-up to this is, what if we had put a battery in? Right? If you put a battery in, you get a little different equation, right? Using Kirchhoff's loop rules, if we go across the battery, we're going to pick up a voltage, and then we'll have a voltage drop across the resistor, then we'll have a voltage drop across the capacitor. And those voltage gains and drops should all add to 0. Now, I is the derivative of charge, is the flow of charge through across any given point. Then we have our Q over C. And let's just chat about this briefly. So rearranging things, we're going to have a Q prime equals a minus 1 over C Q plus V naught over R. Right? Notice this has units of current. It's an initial current. Right? So we can check our units as we go along. Little physical things. I'm sure there's lots of them I'm not mentioning. Now we don't. We can say a lot about this graphically. This is a line, again, with a higher y-intercept. It's at V naught over R, right? And so the previous line went through the origin. That equilibrium has been shifted over here, right? And we can find what that new equilibrium is, setting the current equal to 0 when is the current equal to 0, and solving, where we can get rid of the R. We'll have V naught times C, right? Make sure that works. Yeah. So here's our. This is the equilibrium charge we're going to have in the presence of a battery. So that's kind of nice. Now it's still flowing. If you have between 0 and V naught C, you're going to have a positive derivative. Otherwise, you'll have a negative derivative. So it's still a stable equilibrium, but that equilibrium has been shifted up. But the shape of the solution curves is going to be the same. So that's unnecessary. If this is V naught C, if your solutions were curved like this before, because of this argument of the derivative being negative but decreasing, then you're going to have those same curves here as before. Right? You have 0, you'll have a large positive derivative that decreases. So these are all concave down, these are all concave up. So one of the strengths of this is that adding a term like this, if we understand this concept, adding a term like this shifts the line up, shifts the equilibrium over. The equilibrium corresponds to a horizontal asymptote. So the asymptote increases. This is a Q versus T graph. All the other curves stay the same. The shape of these curves is really dependent upon the value of the derivatives here. Well, this is still a line at the bottom. So whatever is governing the shape of these solution curves stays the same. It's just their position. So that's a potentially valuable insight. Now I should note, let me note a limitation of this. So a limitation of these flows on a line is that if my battery was a function of time, something like V naught sine omega t, right, some sort of alternating current source, I can't deal with this method. Right? I can deal with a constant. I can actually even deal with a variable if it depends upon Q. I'm not sure what that would mean physically, but if my voltage source was somehow sensitive to the charge on the capacitor, I could do something like that. But I can't handle this. We will handle this soon, though, in approximate method with Euler's method. So there are ways of handling this, both explicitly and approximately, but not with this method here. Okay?